Okay, welcome to week 8. We're going to go from association to causation, cover lots of interesting topics. And our first module is on causation criteria and some other frameworks for moving from descriptive epidemiology to more analytic epidemiology and causal inference. So descriptive epidemiology is what we've been doing, mostly what we've been doing since the beginning of the term. We're studying the amount or distribution of disease within a population, gathering data about exposures and outcomes. Now we transition to analytic epidemiology, where we really want to know what's causing disease. And we've studied a couple of different study designs, cohort studies, case control studies, experimental designs that help us start to do that. We actually want to know, why does one group have more disease than another group? How might we prevent or treat those different risk factors to reduce the incidence of disease? So what's our goal with analytic epidemiology? We have an exposure, we have a health outcome, and we basically want to ask the question, are these linked causally? And there's some fundamental questions underlying analytic epidemiology that we should keep in mind. So first, this causal relationship. Does this thing A over here cause this other thing B over there? And if so, how strong is that relationship? Can we actually quantify the magnitude of the association? And once we know there's association, can we actually say how much of the health outcome can be attributed to this exposure? So lung cancer and smoking is a great example. If we know how much lung cancer there is in a population and we know that it looks like smoking is very strongly associated with it, can we say how much of the burden of lung cancer is actually caused by smoking versus other risk factors or other exposures? So how do we establish causality? That is a good question. So one way to do it that's very tidy is an experimental design, and we've talked about why that makes a really good counterfactual, because through our assignment of exposure, random assignment, we can actually say that any difference in outcomes that we see at the end of that experimental design can be attributed to that different treatment that we've assigned. That's very clean. It's a very great clean counterfactual way to do a causal analysis. But as we know, it's often the case that an experiment is not possible or feasible. So what else do? We do observational studies, and again, we've looked at several different kinds: case control and cohort and cross-sectional, and an ecologic study where you're just comparing the different occurrence of two different variables sort of occurring naturally. So there, establishing causality gets a little trickier because we haven't randomly assigned treatment or exposure. Well, let's go back a little bit and think what we mean by a cause. So here's two definitions. A cause is a factor that produces an effect, or a factor that makes a difference. So let's make this a little concrete, literally concrete. Let's think about an elderly woman walking down a concrete sidewalk. She slips, there's ice, she falls, and she breaks her hip. So let's talk about what caused her broken hip. Well, one example we can think of, one model for thinking about causation, is what's called the web of causation. And the example here is breast cancer. We'll return to our lady who fell on the ice in just a second. And we can think about the many factors, some of which are very proximate. They're very near to our outcome of interest, in this case breast cancer. Some of which are much more distal. They're further away, and they involve more steps, more causal mechanisms in this kind of multifactorial web. Some are genetic, physical in nature, some are more social, environmental. But we think of all of them as kind of linked in through this web to an outcome of interest. So if you think for a minute, you can pause the lecture and draw a similar sort of web for our elderly lady with her broken hip. And what are some of the things you think might come into play with that injury? Well, she fell. So there was a fall that actually immediately, most proximately, led to her broken hip. Some reasons for the fall: well, there was this ice that had to happen so that she slipped. Her muscle strength was such that she couldn't break the fall or prevent the fall. She may have been not steady on her feet or had poor equilibrium. In addition, she might have a predisposition through osteoporosis for that fall to actually create a hip fracture. Some people would fall and not break a hip. They would just stand up and walk away. That osteoporosis may have many proximate or distal factors. Certainly we know osteoporosis is related with age, to exercise, to her diet. It may be her access to care. This osteoporosis wasn't diagnosed or treated early, so that she had quite a severe condition that made the hip fracture even more likely. Similarly, exercise and age might be related to her muscle strength. If she has poor equilibrium, that could be something that was genetic, or it could be related to a head trauma. Finally, if we think of environmental factors, she may live in an area that is no longer paying for regular snow removal, such that the ice built up on her sidewalk, and that fall was more likely. So again, multidimensional, multifactor, sort of a web design. Another causal model we think of in epidemiology is called the Chinese box. A lot of people call it an onion pattern as well, where again, the proximate factors are kind of an inner box, maybe the genetic makeup or the physical characteristics or mental temperament or endowments of an individual. The next layer out are choices and behaviors and preferences that interact with those physical attributes and mental attributes. And of course, those behaviors and preferences are situated within an environment, a social environment and a physical environment that's also causing exposures, causing a distribution of exposures, and those exposures are causing outcomes. Okay, so let's get back to our question. So we are very good at running studies. We can calculate a lot of odds ratios and relative risks. Can we say that that link is causal? And here's some quotes from a wonderful researcher who we'll learn a lot more about this week. He said, "More often than not, we're dependent upon our observation and enumeration of defined events for which we then seek antecedents. In other words, we see that event B is associated with the environmental feature A. In what circumstances can we pass from this observed association to a verdict of causation?" And that's from Hill in the mid-60s as president of the Royal Society of Medicine, giving his presidential address, which turned out to be a very long-lived and famous document, sort of outlining some criteria we might think about when we're trying to demonstrate causality. And here's the criteria. There are 9 of them. We'll go through them very briefly, and I've assigned this paper, as an optional reading for the week. It's one of those great documents from epidemiology that's good to know. So when can we say that our association is perhaps causal? Well, one criterion might be the strength of the association. We know that large associations are just more likely to be causal than small ones because they're harder to explain away. And we'll see some great examples of that this week in our case study. Consistency is also nice. Single studies are rarely definitive, is the quote here. We like to be able to say this study has been replicated by different researchers in different populations, different times, different study designs, and that consistent evidence builds a causal argument quite nicely. Specificity is rarely met, but when you do find it, it's a great boost to causal inference. If there's a one-to-one relationship between a specific exposure and a specific outcome, if you only see the one in the presence of the other, that's a very nice, strong causal argument. It's rare. We have a lot of causes that can lead to many diseases or outcomes, such as contaminated milk, and we certainly have diseases, like many forms of cancer, including scrotal cancer, that have many causes. So specificity, again, is lovely. It's rare, and we don't, of course, need it for causal inference, but it's nice. Temporality is a biggie, and we've talked about this before. Because of the universe that we live in, that pretty much time only moves in one direction, we really want to be able to see that the exposure preceded the disease. That's one of the challenges to cross-sectional studies, and of course one of the great joys of cohort studies is that we can follow people for a long time. One example we've talked about is the rising incidence of autism and whether it's related at all to the vaccines that children are receiving, and specifically the mercury that's sometimes used as a preservative. If that were the case, we would want to see that over time, as kids got more mercury in their system from vaccines, that we were seeing more autism. And that's actually quite the opposite of what's really going on. This is a nice graph showing the decline in mercury exposure from vaccine preservatives in the late 80s, early 90s, while the incidence of autism was still climbing. So that's definitely a piece of evidence against the temporal link between mercury exposure and autism. Gradients we've talked about, biological gradients. It's also known as a dose response. So we want to see that as the strength of the association, as the exposure increases, the strength of the association increases too. We'll talk about this again in our case this week with cigarettes and lung cancer. But what we want to see, of course, is that more cigarette smoking, not just yes-no cigarette smoking, but a few cigarettes versus lots of cigarettes, are actually producing a higher risk of the outcome of interest. The next several are a little fuzzier, but I think they're helpful criteria to keep in mind. So plausibility just says, do we have some existing biological or social model to explain the association we see? So, once germ theory came around, it was a lot easier to imagine viruses and bacteria causing disease. Before we had that model, it was harder. So when John Snow was trying to demonstrate that the cholera was caused by a little tiny thing that was in the water, that was hard for people to grasp because that mental model hadn't really taken hold yet. In terms of coherence, which is kind of a similar idea, is the association that we're observing consistent with sort of what we know about the natural history and biology of disease? So I think Gordis talks in some detail about Barry Marshall, who discovered that Helicobacter pylori actually causes peptic ulcers. Again, that idea took him a long time to convince people, that causal association, because that's not how we thought ulcers were developed. We thought they were sort of caused by stress. Experiments, Hill put on his list of criteria, of causal criteria. If we know that we've assigned the exposure to people randomly, then we've got a very strong causal argument that the differences in outcomes we're seeing are related to those exposures. Of course, not always possible. And finally, analogy. So the association between the exposure and disease, does it have characteristics or features that are similar to other things that we know are also considered causal? So when the concern about thalidomide causing birth defects came around, because people knew that rubella as a disease, that if mom contracted rubella during pregnancy, that her child might have birth defects, we could imagine also that a medication that she took might work in utero to harm the child in a similar way. So that analogy was helpful. So if you want to sort of apply these yourself, think back to our Experimental Designs Week when we talked about Alfred Sommer studying vitamin A. And as he set out to demonstrate that vitamin A doses could reduce mortality, he sort of went through a series of studies. We looked at both an observational study and an experimental study he did. And if you think about the various criteria, you might spend some time thinking at what point in his trajectory of studies were the different criteria met, if at all. And when was he able to convince the scientific community that this was indeed a causal relationship? So Hill has some other great quotes, and there's some interesting anecdotes coming out of that story. First of all, he never called them criteria. I think this was sort of an early idea, for his presidential address that became much more codified than he ever imagined. He said, "None of my 9 viewpoints can bring indisputable evidence for or against the cause and effect hypothesis, and none can be required as a sine qua non." So none of them were sort of necessary and sufficient. He also said all scientific work is incomplete, whether it be observational or experimental. All scientific work is liable to be upset or modified by advancing knowledge. And of course, I think we're grateful for the sort of incremental way science works that way. A final sort of take-home message from Hill. What I do not believe is that we can usefully lay down some hard and fast rules of evidence that must be obeyed before we can accept cause and effect. The fundamental question, is there any other way of explaining the set of facts before us? Is there any other answer equally or more likely than cause and effect? And I think this is a really important quote to remember when you are either reading other people's discussion sections in their papers or writing your own. It's very helpful when a causal association has been proposed and demonstrated through analysis to say, here are all the other explanations that could exist for this relationship that we see. Here are all the biases that may have been inherent. Here's a confounder. And then to very systematically rule them out. So yes, it could be a spurious association if XYZ, but here's why XYZ doesn't hold. Keeping in mind that really the best way to demonstrate the cause and effect is to rule out any other competing explanations.